Hello. So this is probably my favourite screencast of the whole course. When I was first given this course to lecture, I started to think, why do mechanisms really happen? Because very often when mechanisms taught, you're taught, well, this is how this molecule reacts with that molecule and the other molecule reacts with that molecule. And I wanted to know the basic fundamental rules that underpinned mechanism so that we could predict them, so that we could work them out as best as possible. And there are these fundamental rules, but I've tried to distill them down in the simplest possible form so that we can work out a huge number of organic reaction mechanisms. And this isn't taught anywhere else. You won't find this in a textbook, but I think it's a really powerful way of thinking about and understanding mechanism. Now, as we've said in a previous lecture, reactivity is controlled by the flow of electrons, and we use curly arrows to represent electron flow. And a bond is formed between the atoms that are linked by a curly arrow. So in the simplest possible terms, if you have something like a Cl-, that's a source of electrons, and it can flow towards a positively charged carbon that has an empty orbital. And we can show that with a curly arrow between the two of them. Two electrons moving from here to here. And in this case, that would give us a product Cl, CH3. So that's an example of a mechanism, the way things are typically taught. This is, of course, the same basic idea when we meet resonance, okay, where we're moving electron density around. But in resonance, you don't ever make completely new bonds or fully break bonds. You just shuffle the electrons around in a molecule. Now, one of the problems with organic mechanisms is they can make it seem like there's a lot to learn in organic chemistry. You'll think, oh, I have to learn all the mechanisms of these reactions. This is not the point of mechanisms. Mechanisms are designed to help you learn organic chemistry. They are predictable. They're based on electronic effects. And once you have a good understanding, you can use them to work out your reactions rather than simply learn them. And in this way, I think that organic mechanism and curly arrows is a key philosophical framework of the subject. A bit like how quantum chemistry underpins the subatomic world, underpinning organic reactivity is the use of curly arrows and mechanistic understanding. And so to help you understand this, as I said at the beginning, I've developed a set of basic rules, and they are my secret to organic chemistry. And really they're quite obvious, it's just they're not very often stated. So our electron flow must start from somewhere good, something electron rich, and our first choice would be a negative charge, something like a Cl-, where we can start the electron flow. Or perhaps an OH-, anything with a negative charge that can give those electrons away. Our second choice would be something with a lone pair of electrons. It's quite electron rich, and they can be donated as a pair of electrons. Something like an amine functional group with a lone pair on the nitrogen, where the electrons can move. Perhaps a water molecule. It has two lone pairs on the oxygen, and we can move one of them with a curly arrow. Our third choice of something electron rich would be a double bond. Something like an alkene, where we can move the double bond towards something that wants the electrons. Perhaps something like a benzene ring. Again, showing it with the alternating double and single bonds allows us to start the mechanism moving from one of these pairs of electrons. And our last choice, the kind of worst option, but it's still a decent option, would be to use a single bond, especially if it's a really weak single bond. One really weak single bond is the peroxide. We met it in an earlier lecture when you were thinking about functional groups, and some of the you do the work related to some specific epoxides that had explosive properties and have been used in some terror attacks. And there, the single bond of the peroxide can break. Or it could be a single bond to something like an OH2 plus, where we can break that bond. Okay, so we're breaking the bonds. And generally we'll apply those in an order of priority. So we'll look first of all for negative charges, then we'll look for lone pairs, then we'll look for multiple bonds, then we'll look for weak single bonds. And that will help us to understand more complex systems. So we've shown the electron flow beginning. Where's the electron flow going to go? Well, the electron flow must move towards something, and it should move towards something good, something that really wants electrons. And our first choice would be a positive charge on a carbon or an H plus atom. Why? These positive charges are associated with empty orbitals. And there's nothing more that an empty orbital wants than a nice pair of electrons in it. So if we can fill up an empty orbital, bingo. So those kinds of positive charges, the carbocation that has 6 electrons, 2 in each bond at the carbon, will quite happily accept a pair of electrons. The proton, if you think about it, a hydrogen with its electron removed has no electrons at all, and it would quite happily form a bond. So those are really the best options for where we want to move our electron density. Our second choice would be adjacent to a positive charge on a heteroatom. Now let's think about what that means. I'll start by drawing you an example of a positive charge on a heteroatom. So it might look something like this. A positively charged oxygen atom. 3 bonds, it's been protonated, its lone pair is being shared with this hydrogen. Now you might think, why don't we just attack the positive charge directly? Okay, but it's important to remember that at this oxygen we already have 2, 4, 6, 8 electrons. And if we attack it directly, it will go up to 10 electrons, and that's just not possible for oxygen to do that. So we're going to attack adjacent to that positive charge, and I'll show you what that means with curly arrows in a minute. Okay. Another example might be protonated water. It has a lone pair of oxygens, but one of its lone pairs has bonded to an H plus. And again, the oxygen here has 8 electrons. As described in the last screencast, the positive charge represents that one of those lone pairs is being shared with an adjacent atom. But the oxygen would love to get back that lone pair that it's sharing, which is the reason it's been left with a positive charge. And if we attack adjacent to the heteroatom, we're able to give the oxygen its lone pair back without ever exceeding the electron count at the oxygen atom. So, for example, we can attack adjacent to that positively charged oxygen and give the oxygen back its lone pair of electrons. Or we can attack adjacent to the positively charged oxygen and give the oxygen back its lone pair of electrons, in this case. Okay? So, we attack either directly at a positive charge, if it's got 6 electrons and an empty orbital, or we attack adjacent to a positive charge if the positive charge has 8 electrons. What about if we don't have a positive charge in the molecule? Well then, we'll look for a partially positive charge. So we'll think about inductive effects and electronegativities. And we look at this alkyl bromide and we think delta plus carbon, delta minus bromine. And so we can attack the delta plus carbon. We look at the carbonyl group and we know the inductive effect through the single bond framework pulls electron density to the oxygen. And so in this case, we can attack the delta plus carbon. Or we think about something like a carboxylic acid. And here we have a delta minus oxygen and a delta plus carbon, and a delta minus oxygen and a delta plus hydrogen. And we could imagine attacking the carbon delta plus or the hydrogen delta plus. And I'll just say here, see later, to know which. We'll explain how when there might be more than one delta plus in a molecule, you begin to choose which one you're going to be attacking, okay? But the basic rule is positive charges and then delta positive charges. Now that's not the end of the story, because our electron flow has to end up going somewhere decent. We cannot end up with 5 bonds at a carbon atom. And electrons like to end up on electronegative atoms. So wherever possible, we will flow electrons onto electronegative atoms in exactly the same way that we did in resonance. Only now, because we're doing mechanism, not resonance, we can break bonds. We don't have to just use the pi framework. We can start to break single bonds as well. So here's an example which begins to look like a real reaction now. We take a hydroxide ion with an alkyl bromide. Where do we start the mechanism? We look for a negative charge. Well, we've got one. Here it is. What's it going to attack? It's going to attack the delta plus carbon. So let's draw in the arrow. There's no positive charge for it to attack. And then we need to flow the electrons onto something good. Break the bond and go on to the bromine. And at this point, I'm not going to write out the full reaction and all the products. We're just thinking about the curly arrows. Where they come from, why they are the way they are. Let's look at a second example. In this case, we're going to think about where's the negative charge? There isn't one. Is there a good lone pair of electrons? Well, there's certainly a nice lone pair of electrons on the nitrogen. Is there a positive charge? No, there isn't. Is there a delta positive? There is. This carbonyl is a really good delta positive, delta negative. So we start our mechanism where the electrons are on the amine lone pair. We move that lone pair to the carbon delta plus, like so. And then we have to flow the electrons onto something good. We flow them onto the oxygen in this case. Okay. So now let's think about putting that into an actual mechanism and drawing the product. We have to make sure, just like in any chemistry that you've done, that we maintain charge in each step of the mechanism. And what we're showing with the curly arrows, we keep as simple as possible. So here's a hydroxide anion, emphasize that negative charge, reacting with an aldehyde. Probably a reaction you don't know, okay? So it's not a reaction we've learned, it's a reaction we're going to work out. OH minus, that's going to be the start for our curly arrows. That's the best source of electrons. It's going to react with the delta plus, delta minus, because there's no positive charges in the molecule, it'll go for the delta plus, and so our curly arrow flows to the delta positive carbon. That would give us 5 bonds at the carbon, and the electron density has to end up somewhere good, and here it can, because we can push a bond onto the oxygen. When you draw the product of a mechanism, change as little as possible. So I will keep the framework of the more complicated molecule exactly how it's drawn. And the little thing, I'm happy to move that around in my reaction. And the OH is becoming attached here to the carbon. And that curly arrow represents that a bond has been made in that position. We've broken a double bond to the oxygen, so we only have a single bond, and we've moved a pair of electrons onto the oxygen, which gives it a negative charge. The charge is conserved. There was a negative charge here and a negative charge there. And there may then be another step to the reaction. You might be told there's a second reagent, and things will continue. But this is how we begin to use curly arrows to work out new reaction processes. It's really powerful, and we're going to keep coming back and using these principles, the basic rules of mechanism, as we go through this course. 1, find your source of electrons. 2, move it somewhere good. 3, make sure the electron density ends up where it really wants to be, which will probably be on an electronegative atom. 3 simple rules, draw them out, keep your drawings simple, balance your charges off. A new arrow makes a new bond, or an arrow from a bond breaks that bond and removes it, and then think about where the electrons have gone. And I'll see you next time, and we'll begin to think about a few more aspects of reaction processes.